You are listening to The Vocal Technologist. Spoken Tech for your ears.
Welcome back, everyone. It's Tech Tuesdays, and we're diving straight into the thick of it. Software engineering, web development, all the latest stuff buzzing around.
Yeah, there's a lot to sift through. We've got performance issues, AI shifts, foundational code debates. Our job today is basically to pull out the really key takeaways, the things you can actually use.
Exactly. Cut through the noise. So let's start with speed. Everyone wants faster apps. What can developers, actually do right now? And maybe what old habits are finally getting tossed out?
Well, a big piece of recent drama and a performance bottleneck for many has centered around styled components. Super popular library, right?
Oh, yeah. Almost everyone's used it or seen it. CSS-in-JS mainstay.
Right. But it hit maintenance mode, and that immediately flagged performance problems, especially for folks using React.
Okay, yeah, I remember the chatter around that. When a tool that foundational slows down, people notice. What was the specific technical snag?
It really became obvious with React 18. The core issue was that style components hadn't implemented a hook called use insertion effect.
Use insertion effect. Okay, let's pause there. For listeners maybe not super deep in React's guts, what does that hook do, and why is leaving it out such a performance killer?
So it's pretty critical. It lets libraries inject styles, like CSS, before React actually makes the changes visible in the browser DOM.
Okay.
If you're doing server-side rendering, which lots of apps are, this prevents that horrible flash of unstyled content, where text appears before it looks right.
Yeah, the FOUC, nasty stuff.
Exactly. So without that hook, the whole rendering process can kind of stall waiting for styles. It's just inefficient.
So a widely used library basically tripped over a newer React feature, but the interesting bit is someone actually stepped up and fixed it.
They did more than fix it. They created a dedicated fast fork. Sanity, the company, they went in, implemented the hook, and added a bunch of other optimizations too.
And the results, were they noticeable?
Noticeable is an understatement. They reported up to 40% faster rendering in some of their apps. 40.
Oh, okay. 40% just from fixing that hook and optimizing. That's huge.
Yeah, and it also sorted out some tricky issues with streaming server-side rendering that were showing up with React 19 previews.
That kind of gain really makes you rethink things. And it maybe brings up a bigger question, this whole term, CSS in JS. Is it even the right term anymore?
That's a fantastic point. The term itself is, well, it's kind of poorly defined and causes a lot of confusion.
How so?
Historically, CSS in JS meant runtime injection. Like JavaScript is literally creating and inserting style tags while the page is running in the user's browser.
And that's where the performance complaints always came from, right? The browser having to recalculate styles constantly.
Precisely. That runtime work is slow. But here's the critical thing. Most popular modern tools people sometimes lump under that umbrella, like Tailwind CSS or StyleX, they don't do that.
They work differently.
Totally different. They're build time tools. They analyze your code during development, generate static CSS files, and those files are loaded normally by the browser. All the heavy lifting happens before the user even gets the page.
So the industry kind of moved past the original performance problem, but we're stuck with the old, maybe scary-sounding name.
Pretty much. The performance concerns about CSS and JS largely apply to that older runtime injection method. For modern build-time tools, it's mostly a non-issue. It's more about understanding how your specific tool works.
Okay, that clarifies a lot. Shifting gears from, compiler magic to maybe coding philosophy. If speed and maintenance are key, sometimes the best advice sounds almost wrong. Like, maybe boring code is actually good code.
Oh, boring is definitely good sometimes. And that lines up perfectly with some recent comments from Linus Torvalds, creator of Linux, Git. He knows about maintaining massive projects.
Yeah, definitely someone who understands long-term code health. What was his take? I'd expect something about extreme optimization.
Actually, almost the opposite. He argued that code needs to be optimized for readability first, making it easy for the next person or even an AI to understand and change it.
Not for, cleverness or minimal lines.
No. He specifically called out overly complex abstractions, things like unnecessary helper functions that just hide simple logic. He said they increase the cognitive load, the mental effort needed to figure out what's going on.
That makes sense. The cost isn't just CPU cycles, it's human brain cycles.
Exactly. And he even mentioned LLMs struggling with that too. His point was, sometimes it's actually better to just repeat a few lines of code rather than creating a complex abstraction you have to trace through multiple files.
Repeat code, that feels counterintuitive. Isn't that technical debt?
It can be, but his argument is pragmatic. If the abstraction is more complex and harder to follow than simply repeating 2 or 3 lines of straightforward code right where you need them, then repeating is better. Reduce the context switching.
So weigh the cost of repetition versus the cost of understanding the abstraction. Pragmatism over dogma.
That's the essence of it. And this idea of pragmatism, of focusing on specific practical value, it's echoing in the AI space too. Remember the huge hype around massive large language models, the LLMs?
Oh yeah, gonna solve everything, right?
Yeah. Well, the enthusiasm is cooling a bit. A lot of companies are finding it hard to get real, tangible, everyday benefits from these giant general-purpose models.
So what's the prediction now?
The focus is shifting towards small language models, SLMs.
SLMs. Okay, smaller makes sense. Is it like, remember early electricity? You had one huge dynamo powering a whole factory with belts.
Yeah.
And the real change came when motors got smaller, specialized, and you could put one right on the drill, one on the lathe.
That's a perfect analogy. SLMs are like that. Highly focused, trained for specific tasks within a company's workflow.
Less solve world hunger, more proofread this report or summarize this meeting.
Exactly. Or maybe rewrite this database query for efficiency. Practical, targeted value without the massive overhead of the giant models. They're proving easier to implement and show ROI on.
Speaking of structure and data, with things like data lakes and tools from Databricks or Snowflake being so popular, is traditional data modeling just...
Not dead, no. Just different. The super rigid upfront modeling has definitely changed because these platforms are more flexible.
But the core ideas still matter.
Absolutely. You still need to understand concepts like, say, fact table granularity. You have to know what the lowest level of detail in your data actually represents, otherwise your analysis is meaningless.
So the underlying principles haven't vanished, it's just the implementation looks different, using technologies like Delta Lake or Apache Iceberg now.
Precisely. The practice evolves, the fundamentals remain. Now, jumping down into the nitty-gritty of infrastructure for a sec, there's a neat solution to a really annoying ID problem, UUIDs.
Ah, UUIDs. Okay, I know UUIDv7 is the new hotness because it's sortable, which databases love. Fast indexing, chronological order.
Right. But the problem is many existing systems, especially older APIs, are hard-coded to expect the look of the classic random-looking UUIDv4.
Yeah, I've hit that. The database wants v7. The API gateway throws an error because it doesn't match the v4 pattern it expects.
The frustrating conflict. So this clever solution emerged, UUIDv47.
UUIDv47. Okay, what's the trick?
It's basically a library or technique that stores the efficient, sortable UUIDv7 internally, but presents a UUID4-style facade to the outside world, like APIs.
So it looks like a v4, but acts like a v7 underneath. How does it do that mapping without being obvious or insecure?
It uses a cryptographic technique. It essentially takes the timestamp part of the v7 and masks it using XOR with a keyed hash stream, like Safhash.
Okay, layman's terms.
Think of it like putting a reversible cryptographic cloak over the timestamp. It scrambles the sequential part using a secret key, making the final ID look random and unpredictable, just like a v4. It fits the v4 format perfectly, passes validation checks, but you can still reverse the process if you have the key to get the original sortable v7 back.
Huh. That is clever. You get database efficiency and API compatibility, solves a real headache.
Definitely. And speaking of platform evolution, we absolutely have to talk about WebAssembly. Wasm 3.0 is rolling out.
Wasm's already a big deal for running non-JavaScript code fast in browsers and servers.
Right.
What's the headline for a 3.0?
It's bringing some major upgrades. 64-bit memory addresses, support for multiple memories, even garbage collection and proper typed references are coming. Big foundational stuff.
Makes it more like a real runtime environment.
Exactly. But arguably the most important feature for its future, especially for broad adoption, is the introduction of a deterministic execution profile.
Deterministic execution. Why is that the killer feature?
Because it guarantees that the exact same Wasm code will produce the exact same result and follow the exact same execution path, no matter where you run it. On a cloud server, in a browser, on a phone, on different operating systems. Identical behavior.
Ah, so it removes that whole category of, well, it works on my machine bugs for Wasm. True portability.
Precisely. That predictability is massive for building reliable cross-platform applications and libraries. It's a cornerstone for Wasm, truly becoming ubiquitous.
Okay, that's huge progress. But sometimes, even with all this advanced tech, simple things go wrong, like that Cloudflare outage back in September 2025. What actually happened there? It took down a lot of services.
Yeah. The postmortem was fascinating because the root cause was almost depressingly simple.
Yeah.
It wasn't some exotic attack. It was a bug in their own dashboard code.
The dashboard took down their core services.
Kind of, yeah. Specifically, it was a faulty React useEffect hook, a piece of front-end code written by one of their developers.
Wait, a use effect? How could that cause a massive outage?
This particular hook apparently got into a state where it started making excessive runaway calls to an internal API called the tenant service.
And the tenant service does what?
It handles API authorization across Cloudflare. So this rogue use effect basically launched a denial of service attack from within their own dashboard against their own authorization system.
Yeah, oh wow.
Yeah, it overwhelmed the tenant service, which then couldn't authorize legitimate API requests, leading to widespread errors across their APIs and dashboard, all from one problematic hook.
That is humbling. A reminder that even the biggest infrastructure can be tripped up by seemingly small front-end issues if they're not carefully managed.
Absolutely. It perfectly sets up our final topic, AI and automation. Because, hey, if human-written hooks cause outages, maybe AI should write the code.
Huh. Well, maybe not all the code. But the research suggests that how we use AI for complex tasks is evolving too. Simply throwing one giant AI at a problem isn't always the best way.
Right. Look at what Anthropic found. They built a system for complex research tasks using multiple AI agents working together.
A multi-agent approach, how did that work?
They used a classic orchestrator worker pattern. A lead researcher AI coordinates several specialized sub-agent AIs. Each sub-agent tackles a different part of the problem in parallel.
Like a team lead delegating tasks.
Exactly. And crucially, they added another specialized agent after them, a citation agent, whose only job was to verify the findings and check sources. It's about distributed reasoning, checking each other's work.
Makes sense. Did it actually perform better than just using one big AI?
Massively better. Their internal test showed the multi-agent system outperforming a single agent by over 90% on complex tasks. Specialization and verification win again.
90%. Okay, that's not trivial. And we're seeing this specialized approach applied to real-world engineering challenges too, right? Like migrating huge legacy code bases.
Yeah, the Monday.com case study is pretty wild. They had this enormous JavaScript client application, a classic monolith.
Mm-hmm.
The estimate to manually migrate it all to TypeScript was something like 8 person-years of developer effort. Just a huge, daunting task.
8 years. Ouch. So what did they do?
They built their own specialized AI system called Morphex, specifically designed to automate breaking down the monolith and handling the TypeScript migration.
Okay, an AI built for one specific massive refactoring job. Did it work? How long did it take?
It worked incredibly well. They completed the entire migration in just 6 months.
6 months, down from an estimate of 8 years.
Yeah, it's a mind-blowing speed up. Shows the potential power of targeted AI automation for these kinds of large-scale, repetitive engineering tasks.
But surely they didn't just, like, press a button and let the AI rewrite everything unsupervised. That sounds terrifying.
Oh, definitely not. It was very much a hybrid approach. Morphex handled the deterministic parts of the code transformation and orchestration, but they built in strict validation checks at every single stage.
And human checks.
Absolutely essential. They had a system they called human totos. When the AI got stuck or encountered code that needed nuanced judgment, it flagged it for a human developer to review and decide the best path forward. AI assistance, not AI replacement, with humans firmly in the loop.
That human oversight seems critical, especially when you consider the known biases in AI models.
A huge factor. There's this well-documented, weird bias, Western-educated, industrialized, rich, democratic. The data these models are trained on often reflects that specific worldview.
Which means the AI's outputs or analyses might be skewed or just plain wrong when applied in different cultural or economic context, right?
Exactly. If you deploy an AI tool globally without accounting for this, you can get seriously flawed insights or make bad business decisions.
So for developers using these tools, what's the takeaway? How do you guard against that bias?
It really comes down to being deliberate. You need to use context-rich methods. Maybe that means actively collaborating with local teams or partners who understand the specific environment. You might need cultural awareness training. Essentially, you have to consciously work to counteract the model's default biases by feeding it better, more relevant context for the specific situation.
Wow, okay. We've covered a ton. From a 40% speed boost by forking a library, to Linus Torvalds saying repeat yourself sometimes, to specialized AIs migrating code bases years faster.
To Wasm becoming truly portable and UUIDs getting clever cryptographic cloaks.
Yeah. It feels like there's this convergence, cutting-edge stuff like Wasm and multi-agent AI, but also a return to basics. Simple, readable code, security, and maybe double-checking your React hooks so they don't crash the internet.
And that brings us right back to the human element, the foundation everything is built on. It's maybe the most critical point for you, our listener, today. While we're building these amazing AI systems and optimizing frameworks, the core human-maintained open-source infrastructure is often struggling.
What do you mean specifically?
I mean projects like curl. Absolutely fundamental, used everywhere. But the maintainer is facing an overwhelming burden, constant demands for support, compliance paperwork, even dealing with floods of often low-quality AI-generated bug reports.
So the tool everyone relies on, the foundation for so much modern software and even AI development, is kind of drowning.
That's the reality. The companies getting immense value from curl often aren't contributing back proportionally, whether that's code, documentation, or just funding.
Right.
The human maintainer is stretched incredibly thin. We touched on this on the Vocal Technologist before, the sustainability issue.
It's a stark contrast. AI automating migrations while the human maintainers of the tools enabling it are overwhelmed.
Which leads to a final thought, maybe a challenge for you listening. If these powerful AI systems, these complex enterprise applications, are ultimately only as reliable as the human infrastructure and the open source ecosystems they depend on, what's your responsibility? How can you as a developer contribute back to keeping those boring but absolutely essential tools healthy and sustainable?
Something important to think about. That's all the time we have for today. Thanks for tuning in, and we'll catch you on the next one.
Spoken Tech, for your ears.